and really just stepped out, but I'd like to thank him and the organizing committee for the invitation to speak at the workshop. I'm not sure why he couldn't read the 5-page CV that I sent him for the introduction, but I guess he decided that was a bit too long. No, actually, I actually shortened it quite a bit for him to read. So what I'm going to talk about today is groundwater, and really give an introduction, I guess, to groundwater as a resource and some of the issues surrounding groundwater. And I'm going to take about 35 minutes or so. So at the end, I think where I would like to leave some time for questions and some discussion. So I want to start off with this little bit of history, I guess, in terms of groundwater. And this doesn't relate to Atlantic Canada at all, and it's actually, I guess, a decision that was made in 1904 in Texas, where there was Mr. East, who had a well on the property, and the Houston and Texas Central Railway dug a well at that time on the adjacent property, and they were using the water for their machine shop and so on. It was the rail yard, and that caused Mr. East's well to go dry. And he sued the railway company for damages because of that. But the court decision ruled in favor of the railway company. And part of that decision is given here, part of the quote, in terms of the movement of groundwater and the understanding at that time, 110 years ago, was that it was so secret, occult, and concealed that any attempt to administer any set of legal rules would result in hopeless uncertainty and therefore would be practically impossible. So that sort of gives you a picture of sort of people's views of groundwater hydrology, or hydrogeology, as we call the sort of scientific discipline that deals with groundwater at that time. Some people, I suppose, may still hold that view, but I guess I'd like to give you some insight into groundwater as a resource and our understanding of how groundwater works and so on, because we're 110 years past this decision and must advance in our understanding of groundwater as a resource and as a water supply. So I'm going to go through, I guess, 4 major points in my presentation. Groundwater as a resource, how we use it, where is it used, particularly in Atlantic Canada. The hydrologic cycle and aquifers, examples of the consequences of intensive land use on groundwater resources, and some points, I guess, or some ideas in terms of groundwater management and some concluding remarks. So groundwater is a resource, like many of the other resources that we have, the soils and so on that we use for agriculture, a resource. It's a water resource, of course. And it can be renewable or considered as non-renewable. It depends, I guess, really on how it's being used and how it's being managed. I think in most of Canada, we get quite a bit of precipitation and therefore recharge of the groundwater aquifers, and we'd like to manage our groundwater resources as being renewable. In some arid areas of the world, they're really non-renewable. Groundwater is being mined, essentially, for whatever use it may be. And is not being renewed at the rate it's being used at. But in general, groundwater is widely available, generally of good quality, which means that it can be used typically with minimal amount of treatment, and it's relatively inexpensive to access the groundwater resource. So those are all good qualities of groundwater. And in many parts of the world, there's really no alternative to using groundwater as a freshwater supply. So in the Canadian context, groundwater is important. It's estimated that almost 10 million Canadians use groundwater as their primary source of drinking water. And in the rural population, that percentage is about 80%, is the estimate, in terms of rural Canada, in terms of their water supply. So it has particular relevance in the rural regions. In Atlantic Canada, if we look at that, of course, in PEI, many of you will be aware of the fact that 100% of the population is supplied by groundwater, so it's a highly important water resource on PEI, including about 12 municipalities. In New Brunswick, it's about 67%, or about 2/3 of the population, relies on groundwater as the water supply, including 58 municipalities. So there's, for example, the city of Fredericton, where I live, is entirely supplied by groundwater. In Nova Scotia, it's about 46% of the population. In Newfoundland and Labrador, it's about 34% of the population. So Atlantic Canada, if you look at the Atlantic provinces as a whole, or as a region, groundwater supply is quite important for water supply, perhaps more so than other regions in Canada. Now there's a map here with a lot of dots on it. But it shows New Brunswick, Nova Scotia, the island of Newfoundland, and it also shows South Shore of the St. Lawrence and the Gaspé Peninsula as well. These are data that have been compiled from what we call high-capacity or multi-user well yields. So there's a couple of things when you look at this map or this distribution of dots that you should realize. The first one is these are really community water supplies, so we're not showing on this map individual domestic wells. What we're showing really is where the population is, so where these wells are, where there's populations. And there's a color scale up on the left-hand corner there, where the small blue dot is a well yield, individual well yield of less than 3 liters per second. That's equivalent to about 40 gallons per minute, roughly, if you think in gallons per minute. Then there's a slightly larger blue dot, and then the dark blue dot. So between 3 and 10. And 10 liters per second is about 140 gallons per minute. And then there's the open red circle there, right here, which is over 50 liters per second from the individual well. So these are very high productive wells. And what you see, for example, you can really not see PEI. It's kind of obliterated with all the dots there. So very productive aquifer here in PEI, basically over the whole island. In other provinces, it tends to be more localized. So for example, those of you from New Brunswick may recognize the St. John River Valley. It's really being traced out by a series of dots here. Down here. So that sort of string of dots there, starting up at the border with Quebec and going down through Fredericton, is really the sand and gravel aquifers that occupy the St. John River Valley. And those are highly productive aquifers that are used for water supply. In eastern New Brunswick, we have the same, more or less the same sandstone aquifer formations that we have here in PEI. So this is governed, again, this map is really governed by where are the people living, where they're using high quantities of water for communities and cities and so on, but also by the geology. Right? Where is the geology favorable for groundwater, and where are the good aquifers, as we call them. In contrast, if you look at Newfoundland, almost every dot over there is less than 3 liters per second in terms of well yield, and in most cases it's substantially less than 3 liters per second. So we just don't have the same types of geological conditions that allow for the large well yields that we have in PEI and Brunswick and many areas in Nova Scotia as well. So groundwater is used for municipal supply, domestic supply. Globally, groundwater plays a major role in agriculture. It's estimated, for example, that about 70% of all the groundwater that's extracted in the U.S. is used for irrigation. So it's a major component of the use of groundwater in the U.S. And the other point on this slide is that the natural discharge of groundwater supports ecosystems. So whether it's streams or wetlands or whatever, that's a component of the water flow that goes into those ecosystems, and therefore it's important from that perspective as well. So let's just look at a bit of, hydrology in terms of where the water is coming from that forms groundwater and where it resides. So the diagram on the left there is intended to depict what we call the hydrologic cycle. It's simply the cycling of water through the atmosphere. falling as precipitation on the land, and then infiltrating. Some component of that infiltrates into the ground surface and moves downward, forming what we call groundwater. So groundwater is actually a very large portion of the fresh water that's on the earth. If we look at the little column on the right-hand side, that's depicting, just with those three color scales there, fresh water. The bottom, the base of that, is actually glaciers and ice caps. So most of the fresh water is actually in solid form on the earth. So this is a global sort of estimate. The next brown piece there, about 30%, is groundwater, fresh groundwater. And the little slice on the top, the blue slice on the top over on the right-hand side, is actually surface water and other fresh water. So that's a little more than 1%. So in terms of the reserve of fresh water, groundwater is a very significant portion of that. It's a major component of the sort of the hydrologic cycle on the earth. So groundwater sits in aquifers, and aquifers is just a term that we use to describe the geological units that can store the water. So they have porosity, they have pore spaces or fractures that allow the water to fill those pore spaces, and they can also allow the water to flow through them. So when we look at groundwater, it's not just a stagnant reservoir of water that's sitting there. It's in motion, although slowly. Aquifers can be small, large, shallow, or deep. They can occur at different depths and different locations. And the residence time, or the time that the water spends in the ground or in the aquifer, can vary from years to millennia or thousands of years. And that's kind of depicted on that diagram on the right. So there's two things I want to point out there. At the top, in the uplands, or the treed area there in this diagram, we have what's called a recharge area, and that's typically where the water is moving downward. It's infiltrating and moving down to the water table, and then it moves in the aquifer due to gravity principally. It's moving, water flows downhill, so it does so pretty much underground as well. So it's moving through the aquifers and then discharging. On the right-hand side, it shows a stream. We would call that a discharge area because the water would tend to be moving up into that, that setting. So there's different paths shown with those blue arrows and different times. So we might be talking about years for the water to move from the recharge area to the discharge area. If it goes deeper in the system, it could be hundreds of years. So it really depends on the geology and the permeability of these units. So there's a little diagram here sort of depicting that. If we look at the hydrologic cycle and try to put a time scale on the top there, so 1 day, 1 year, 100 years, 10,000 years, water in the atmosphere is on the lower end of the scale, and maybe rivers a little further up, wetlands and lakes, but groundwater can span quite a large time scale there, and it's typically much longer than we think about water residing in a river or in a lake. Okay? So it's got a longer time scale associated with it. So recharge is the source of water, the mechanism that water enters into the aquifer. And in Atlantic Canada, the recharge is mainly an infiltration of snowmelt, water in the spring, and also rainfall. So this is from a research study in central New Brunswick, where we're looking at the sort of monthly distribution of recharge for different time periods. And what I just want to point out here, this is just a percentage. So the axis here is the mean monthly recharge as a percent of the annual recharge. So what we're showing, for example, in April, there's different scenarios here. So we were actually looking at climate change and how that might influence groundwater recharge. But the reference period here is 1961 to 2000. So that's the black bars that you see. And I'll just point out that in April, for example, we get about 40% of the annual recharge in that month. Okay? So it's not like we get recharge sort of consistently. We get it sort of in certain periods of the year, we get most of the recharge. And that tends to be in the spring, April, May, and then later in October, November, where we get increased precipitation, lower temperatures, less evapotranspiration, and all that type of thing. So we get it sort of at different periods, and really January, February, in a typical year, there's not much recharge at all. The other end of the spectrum, or the other side of the aquifer, the discharge period, this is an example from the Wilmot River here in central PEI for the year, I think it's 2008, so it's going from January 2008 to January 2009. And this is showing, the black line is the total flow in the Wilmot River at the hydrometric station, or the gauging station. And the red line is an estimate of what we call base flow, or the groundwater contribution to the total flow. So you'll see in the spring, it's you see the peaky nature of the flow. You get high discharges. A lot of that's surface runoff or snowmelt runoff directly into the stream. But you see this sort of fairly significant component through most of the year, especially in the summer period, where groundwater, in fact, makes up the majority of the water that's in the stream. So we call that base flow, and that provides, the sort of constant discharge to many of the streams and rivers in the region. So I just want to talk briefly about development of an aquifer, use of an aquifer for water supply. So we have this very simple diagram on the top there. We have recharge occurring through whatever landscape is above the aquifer. So there's two arrows. Recharge is the water going in, discharge is the water leaving. So let's say we imagine that we're going to pump that water for water supply. So we put a well in, and this is just a cartoon depiction of this. So we're going to extract a certain amount of that recharge water. Pumping, by and large, with very few exceptions, does not affect the amount of recharge. Okay? The recharge is fixed by the climate, right? What happens on the ground surface. So, I mean, you can just, this is the take-home exam here. What happens, if this is the scenario, if we start extracting groundwater and we don't adjust the recharge, what happens to the other component that we're looking at here? So, being the discharge, right? So there's only one possible thing that can happen if we reach a new equilibrium. That is, the discharge will decrease, right? So we're using that water, taking it out of the aquifer. So that's a very simple water balance sort of scenario for an aquifer that can happen. That's assuming now that extracted water is not returned to the aquifer in any form, right? It's used, consumptive use we call it. So pumping wells first draw water from what we call storage. So when we start to pump, we drain the water-filled pores and the fractures that are close to the well. And then gradually, it takes time for that to occur, and then gradually we start to capture groundwater flow that would have otherwise discharged from the aquifer. So normal discharge into surface water typically. And if the pumping rate or the duration of pumping is long enough, we may actually reverse the flow. We may actually cause surface water to flow into the aquifer. So we reverse the hydraulic direction of flow there. And that's shown in this simple sort of schematic diagram here where we have a shallow aquifer, okay, and a stream. You see just the edge of the stream bank on the right-hand side there. Again, the arrows show groundwater moving from the recharge area on the left, the upland area, discharging into the stream. We put a well in there that's a fairly deep well, goes sort of right to the bottom of the aquifer. So initially we're drawing water from the aquifer close to the well, or from storage, and we get a bit of drawdown around the well, which is shown there sort of on the cartoon. And we still may have the water flowing into the stream, so we're just sort of intercepting some of that water. And as we continue pumping, then we draw down a little more, and we may reach an equilibrium where we still have some base flow into the stream, and we're using the water for some use. But there are situations where if we continue to pump at excessive rates or rates that are, or continuously pumping, so the rate and the duration makes a difference, we might actually reverse the flow direction. So we might actually cause surface water to infiltrate into the aquifer, and some of the water drawn from that well will in fact be surface water. So when the storage is no longer a source of water to the well, then basically the pumping of groundwater will result in decreased stream flow, either by capturing discharge that would have naturally gone into the stream or inducing infiltration, reversing the flow direction. It takes time for that to happen. It doesn't occur instantaneously. It also takes time for the situation to recover and reverse if the pumping stops. And there's a number of factors which I'm not going to go into today other than just to list them. The distance of the well from the stream, the aquifer properties, how permeable they are, the pumping pattern, is it continuous pumping or is it intermittent pumping for short periods? They all can play a role and will play a role, and one of the speakers, I think, in session A will be talking in more detail about that. Now, I want to go into a couple of examples. And the first one is related to groundwater extraction, just sort of this idea that we talked about here. And it's really demonstrating the cumulative impact of multiple pumping wells and how significant that can be. And so my argument is that on fairly large scales, pumping needs to be assessed, first of all, what's the impact of pumping, and also managed. And I'm using this example from western Kansas for a couple of reasons. It's a very well-documented sort of case history about the impact of large-scale well pumping. And it relates, I guess, to a lot of what you're interested in. It's groundwater use for irrigation, so it's a very agriculturally productive area of the U.S. It's what we characterize as a semi-arid climate, but it overlies the High Plains Aquifer, which is, I know here, one of the major aquifers in North America. It's probably, you could say, the world. It's a very large aquifer system. So we have the map on the right there, which shows Texas down on the bottom and South Dakota up on the top there. What's outlined in red is called the High Plains Aquifer. And the area of that is about the size of the state of California. So we're talking a huge aquifer. It's a huge water resource. It's generally water of very good quality. And it's a productive aquifer, as I mentioned, used heavily for irrigation. There's colored squares inside. Those are the counties. The darker the square just means the more groundwater used for irrigation in that area. So it's variable, the use. But I want to just sort of focus on Kansas here, which I just outlined in blue. There's no scale on this map, but east-west, Kansas is about 750 kilometers. North-south, it's about 300 or 350 kilometers. That's sort of the scale. And if you look at the region of the High Plains Aquifer that lies within the state of Kansas, again, the red portion that lies in that sort of blue rectangle there, that's about the size of PEI and New Brunswick combined. If you put them together, that's sort of the land area that you're talking about there. So it's a pretty large scale system. So there's a couple of trends shown on this graph that is from a reference. There's many sort of papers and case studies written about water allocation and groundwater use in Kansas. The line that we can focus on is the red one for now. That indicates the number of groundwater rights that were issued, and principally these are for irrigation. By and large, the groundwater use in western Kansas is for irrigation. I think it's something like 85 or 90% of all groundwater use is for irrigation, so practically we're talking about these water rights being for water rights for irrigation uses. And they started keeping records back in the 1940s. And if you look at the trend, you can see through really starting in the mid-1950s to about 1975, 1980, there's a huge increase in the number of groundwater rights that were issued. By 1975, it's something like 25,000 groundwater rights were issued just in that portion of the aquifer that lies within the state of Kansas. Then you see things sort of start to stabilize there a little bit, starting in 1975 and 1980, because really there's a sort of whole complex history of what's going on here, but really through the 50s, 60s, and 70s, the water rights were being allocated, but there was really no sort of big picture look at what's going on. How sustainable is this, okay, in terms of our groundwater supply, the groundwater supply from that aquifer. Then in the 70s and 80s, people began to realize, well, there's some problems occurring here. So we have to, we have to look at a more holistic or sustainable view of the groundwater resource. So there's several impacts. This is kind of a fuzzy graph on the bottom there, but it shows water depth in a monitoring well in central Kansas, and this is one of the areas where some of the larger irrigation pumping has occurred. The water table depth, if you want to think about feet, is on the left-hand side there. So back in 1950 or so, the water table depth of this particular monitoring well was about 125 feet or something like that. By about 2007, it was 300 feet. Right, so that's significant. Those are major. This is an extreme case I'm showing you here to sort of learn from a bad example, let's say, of what might happen. But it was also estimated that by the 1970s, mid-1970s, that the cumulative quantity of pumping was about 14 times greater than the volume of water that was recharging on an annual basis. So there's no way you can sustain that, right? You're going to have major drawdowns of aquifers if you're pumping at much more than the recharge rate. And again, there's lots of things, legal issues in terms of water rights and all those types of things that relate to this. But one of the hydrologic factors was there was really an overestimation of the amount of recharge that was occurring to the aquifer. So there was indeed less recharge than what they had thought was actually happening. There was no real assessment of the cumulative impact of the pumping. The other thing is, I said that groundwater is connected to surface water. And this is a map produced by the Kansas Department of Agriculture. It compares perennial stream distribution in the state in 1961 and in 2009, I guess it is, 2009. So it's comparing 61 to 2009. So you see in the western part of the state, those portions of streams and rivers that are marked in red were perennial streams and rivers. They flow, there's water in them all year round. Back in 1961. In 2009, they're no longer perennial streams and rivers. They're intermittent streams and rivers. So, I mean, this is the reduction in base flow that I was talking about earlier, and this is a very extreme case. Again, the scale there, north-south on the left-hand side here is about 350 kilometers, and you're talking a huge area in which there's large-scale impact of surface water due to groundwater pumping, right, because of the connection between surface water and groundwater discharge. Now, again, I'll have to sort of qualify this. This is a good example to show of how things can go wrong. I'm not at all suggesting that irrigation, is a negative thing. It's very positive things in terms of food production, particularly globally. But from a water resource management perspective, I mean, these are the types of things that we would be concerned about if things aren't controlled, if things aren't understood, the aquifers aren't understood, and groundwater extraction quantities aren't monitored and traced through time. The other issue that I want to bring up is groundwater quality. For at least 4 decades, hydrogeologists and groundwater hydrologists have recognized that certain activities on the land surface have the potential to affect groundwater quality. Again, there's a cartoon here on the bottom which sort of shows conceptually how we think about this. There's on the left-hand side, there's a waste disposal site, let's say an old rural landfill, unregulated landfill, where we have precipitation and stuff moving through that. Can pick up contaminants, and those move with that infiltration process down into the aquifer. On the right-hand side, it's showing what we call non-point sources, which might be fertilizer use, say, on agricultural land, which is over a fairly large area. So these are issues which, in terms of sort of groundwater quality, are important in areas where typically there's any high-intensity activity which has the potential to release what might be contaminants. And many of you are probably well aware of 2 examples in Atlantic Canada where nitrate is an issue in groundwater in Kings County, Nova Scotia, which is the map on the upper right-hand side there. Nova Scotia Department of Environment has for many decades I think 3 decades probably, been sampling wells in that area. It's a fairly productive agricultural area. These are the most recent statistics there in the upper left-hand corner. So about 23% of the wells, 120 wells that were tested, had nitrate in excess of the Canadian Drinking Water Guidelines. And those of you from PEI, of course, are probably well familiar with the issue of PEI in terms of high-intensity agriculture affecting groundwater quality, particularly from the point of view of nitrate. And nitrate's a fairly mobile solute. Once it gets into water, it typically moves with the water. It's not filtered out in any way or anything like that. Again, we have this connection between groundwater and surface water, and that's particularly evident here in PEI because of the high base flow contributions to streams and direct groundwater discharge to the estuaries and so on that we have. The lower left-hand photograph there is sea lettuce, which is particularly susceptible to high nitrate loading. It really takes off when it gets nitrogen, and that's one of the consequences of the transfer of nitrate through groundwater into the small estuaries that are around PEI, or many of the small estuaries that are around PEI. We've also done some research work on that, and we've been looking at sort of what's the relative contributions, roughly, of nitrate loading to PEI estuaries. And again, that bar chart on the right is just percent of the total loading. So we estimate about 30% is what we call rapid flow. So that's water that would kind of move through the watershed within a year, or less than a year. So that could be surface water or very shallow groundwater. There might actually be some groundwater in that 30%. And about 70% is what we call delayed flow, or that's water that takes more than a year to move through the system. So that would be deeper groundwater moving through the aquifers and discharging into the streams or into the estuaries directly. So there's this delay or lag time. So there's an implication here. If we change land use in any way, we may not see the result in the discharge area, the surface water, that year or next year or 5 years down the road. Right? There may be a time lag in terms of what happens in the system because of the flow of groundwater through the aquifers. Okay, so I'm just going to conclude with, I guess, a few points on groundwater management. This Council of Canadian Academies report, I was on the committee that was produced this report. We sort of looked at, it was basically a study of what's the sustainability issues for groundwater in Canada. And I want to point out that there's lots of issues that groundwater hydrologists or water resource managers might be concerned about. Climate change and other energy and mining activity. I'm from New Brunswick, and if you're in New Brunswick now, shale gas is #1 on the radar screen from everybody's point of view in terms of groundwater contamination or groundwater use for fracking and all that type of thing. So this was kind of meant to be a national perspective on what are the issues facing groundwater, I guess, of the sustainable management of groundwater. But as part of that work, we came up with this diagram, which really comes down to what are the sustainability goals for groundwater. And these could be set by local watershed groups. In the case of Kansas, to deal with the severe depletion problem, they set up groundwater management zones. And these were really areas that overlie those aquifer regions within Kansas, and they were sort of local management districts for the groundwater supply. So who decides these goals can vary from local watershed group to provincial government or special organizations that are set up. So you can see there's a number here down the lower left-hand corner. There's achievement of economic and social well-being. It's realized that, again, groundwater is a resource. It can be put to economic and social benefits, whether that's agricultural production, for example. Going around clockwise, and we have protection of groundwater from contamination. Surely we would like to achieve that as a goal. Protection of ecosystem health at the top. That doesn't mean it's the top priority. These are all sort of, the priority here has to be decided by the users and the people in the areas. Protection of groundwater supplies from depletion, and application of good governance. That just means that stakeholders should have a say in their water resources, how they're going to be used, how are we going to decide on these priorities and what's the allocation going to be of groundwater. So in conclusion then, I just want to point out a couple of things. Going back to that first quote that I had from that court decision in Texas, groundwater is not an occult science or anything like that. So I'm Dr. MacQuarrie and I deal with groundwater. That doesn't mean I'm a witch doctor or anything like that. I mean, groundwater hydrology is a well-developed science. And in the last 20 or 30 years, there's been significant advances in our understanding of how groundwater works and methods to assess, flows and quality and so on. I haven't really gone into those. Subsequent speakers here are going to talk about different methods that are used in groundwater studies. So I would say that the science is fairly well advanced. In terms of extraction, groundwater extraction should be expected to have some impact on surface water. There's really no getting around that. I mean, it's just the hydrologic balance, the way things work. The magnitude of the impact is what really we have to worry about. It could be a negligible impact. It might not be significant to any ecosystem or any base flow component or whatever, and that depends on the pumping that's going to occur, amounts, locations, and so on, and the aquifer properties. What's the storage capacity of the aquifer? What's its propensity to recharge? Is it recharged on an annual basis that's sufficient for the amount of pumping? Groundwater monitoring, and by that I mean the whole sort of spectrum. Things from extraction rates to recharge rates of the aquifers, groundwater levels and groundwater qualities, absolutely essential for management. It's the old saying that if you can't measure it, you can't manage it. Well, that's certainly true, and that sort of example from Kansas really illustrates that unless you know what's going on in terms of extraction rates, unless you understand recharge to the aquifer and so on, you're likely not to be able to manage the resource. Some aquifer types, like the fractured rock that we have here in PEI, for example, there's some challenges, definitely technical challenges there in monitoring, for example, contamination or quality, but there's research, it's an active area of research, and advances are being made in that, so it's not like it's a stagnant field, there's active research on that. And I would say, I guess my last point is, because of these combined effects, there's a number of things relative to groundwater that we should keep in mind. The first one is cumulative impacts. So often we're talking about what's happening on a fairly large landscape, right, affecting the groundwater quality, maybe not one individual property having such an impact, but when you look at cumulatively what's going on in a larger area or a watershed, that's important. The other thing is the long residence time. So we're looking at times that we're, perhaps not planning for or thinking about in terms of years or decades for things to change after we do something. So that's definitely a bit different maybe than thinking about, how fast the water is moving through a stream or a river. And also groundwater surface water interactions. So it's not just the aquifer itself, it's the surface waters that may be fed from those aquifers that are all important. So I would contend that those 3 points and others means that groundwater management needs to be really carried out at relatively large time and spatial scales. Right? We're probably not looking at changing something this year and having an impact next year. It could be years to decades. And we could be looking at watershed scale to entire aquifers. So it requires a coordinated approach, integrated approach, and long time frame, longer than perhaps what we're used to working with in other water resource components. So I'd just like to make some acknowledgments here. I presented a few bits of research from some graduate students and so on. These are some of the supporting organizations who have funded groundwater research, some of which I've shown here. And I'd like to thank you for your attention.